Hello, my name is Jamie Schiffer, and I am a graduate student in the Amaro Lab at UC San Diego studying the dynamics of T4 lysozyme L99A mutant. The T4 lysozyme L99A mutant is a model system for studying transitions between ground and excited states of proteins, as well as studying ligand binding to buried cavities. Here is an image focusing on the C-terminal domain of the L99A mutant. In blue is the cavity that is shown for a ground state structure, where in orange is the cavity shape in an excited state. So in this protein, there's a buried cavity that is able to bind ligands, but also contributes to ground to excited state transitions. This protein has been studied for over 20 years. And while it is, in that way, an old protein, there are much interesting things that we can learn from this system. Just as the story of a 75-year-old balloon salesman was able to reveal an incredible amount of insight into the human condition, so too can this story about the L99A mutant of T4 lysozyme reveal unique insight into the dynamics of buried cavities in proteins. Here we are reviewing the results from a simulation that captures the transition from the ground to the excited state of the T4 lysozyme L99A mutant that was performed on the Anton supercomputer. On the left is a graph showing on the x-axis the time of the simulation in microseconds, and on the y is the distance between different residues. So in black it's between valine 103 and phenylalanine 114, and in blue it's between valine 87 and phenylalanine 114. And phenylalanine is shown in the image on the right. That is the residue spinning around, coming out of the pocket, snapping back in and out, and finally finding its resting place in the buried pocket of the L99A mutant, which is a cavity-forming mutant of T4 lysozyme. What's interesting is that the results from this simulation reveal multiple metastates as well as an intermediate state in the transition between the ground and the excited state. Back-calculated chemical shift differences between these two states align very well with experiment results. So on the x-axis here is the residue number. The y-axis is the chemical shift difference between the ground and the excited state. And above this graph, you can see the different secondary structures in the C-terminal domain of the L99A mutant. So this is exciting. Here on the left is showing a graph with the x-axis being the time again of the simulation, and on the y-axis is the volume of the buried cavity that we measured using PAVME 2.0, a program developed in the Amaro Lab. And on the right is showing the results from these calculations. These are showing the changes in shape and size of the buried pocket as the trajectory moves from ground state at 0 microseconds to the excited state at 27 microseconds. This reminds me a lot of when I was taking art when I was very young, and the teacher told me to focus on the empty space because this is where the most interesting things lied. It's the same thing here for our protein L99A. The empty space explains a lot about the dynamics.